All right, let's just dive right into this. Welcome to this quick revision session where, for today, I am stepping in as your high-stakes coach. We are going to lock down the 5 chemical properties of metals for your final exams. Look, if you've been struggling to remember which metal does what, when, and under what temperature, you are in the exact right place. This explainer is all about rapid-fire recall. I'm going to give you the logical shortcuts and the expert tips you need, so you don't just memorize things, but you actually understand the reactivity trends. By the time we're done here, you're going to be able to identify unknown metal samples during your practical exams with absolute confidence.
So here is your rapid-fire exam checklist for today. 1. Oxygen and amphoteric oxides. 2. Water, cold versus hot. 3. Dilute acids and salts. 4. Displacement dynamics. And 5. Hydrogen exceptions. Let's not waste any time.
Section 1. Oxygen and amphoteric oxides.
Okay, let's break down the reactivity series into a really simple 3-tier logical shortcut. To memorize the order from top to bottom, just remember this fun little mnemonic for the metals we're looking at here. Please, send, monkeys, and zebras, gold, right? So at the very top, we have potassium and sodium. These are your highly reactive metals, and they react violently with oxygen to form potassium oxide and sodium oxide. Literally, you just leave them out in the air and boom, they react. Then stepping down to the middle tier, you've got magnesium, aluminum, and zinc. When they react with oxygen, they don't just burn away indiscriminately. Instead, they form a thin, highly protective oxide layer right on their surface. And this layer is brilliant because it actually protects the inner, unreacted parts of the metal from further oxidation. And finally, sitting at the bottom of the ladder, we have our non-reactive metals like gold and silver. They just sit there. They do absolutely nothing when exposed to oxygen. So if you're handed an unknown metal in a practical exam and it simply doesn't tarnish or react in the air, you are almost certainly looking at the bottom of this table.
Now, the crucial point to remember is that metals usually form basic oxides. And if you recall your basic chemistry tests, basic oxides turn red litmus paper blue. But here is a classic exam trap I see students fall into time and time again. Since most metal oxides are basic, do they all turn red litmus paper blue? Are there any sneaky exceptions hiding in that middle tier of our reactivity series?
Well, actually, the answer is a massive no. And this brilliantly illustrates exactly why you need to watch out for zinc and aluminum. These metals form what we call amphoteric oxides. Amphoteric is just a fancy chemistry term that means they display both acidic and basic properties. Zinc oxide and aluminum oxide are your prime go-to examples here. If a test question ever asks for an exception to the basic oxide rule, this is your silver bullet. Memorize these 2 amphoteric exceptions, and for sure, you'll save yourself crucial points on exam day.
All right, moving on to Section 2. Water, cold versus hot.
I'm going to give you a huge shortcut for predicting metal reactions with water, and it's based strictly on temperature. So the general rule of thumb is that metals react with water to form a metal hydroxide and hydrogen gas. But temperature changes the whole shebang. Think about our highly reactive trio, potassium, sodium, and calcium. They are so incredibly eager to react that they only need cold water. Drop them in cold water, and they immediately form metal hydroxides, like sodium hydroxide or calcium hydroxide, and release a bunch of hydrogen gas. But then, look at our moderately reactive metals, magnesium and zinc. They're a bit more stubborn, right? They won't react with cold water at all. If you're in a practical exam and your unknown metal does absolutely nothing in cold water, but suddenly reacts when you heat it up, you've likely got magnesium or zinc. And here is the biggest trap of all. When they react with hot water, they do not form hydroxides. They form their respective metal oxides, like magnesium oxide, plus hydrogen gas. So remember, hot water equals oxides. Cold water equals hydroxides. You've got to lock that shortcut in.
Section 3. Dilute acids and salts.
Okay, let's dive into this fairly simple equation. The golden rule to recall here is that reactive metals combine with dilute acids, think sulfuric or hydrochloric acid, to vigorously create a metallic salt and release hydrogen gas. Literally, whenever you see a reactive metal paired with a dilute acid on a test, your brain should immediately start screaming, salt plus hydrogen. Let's see how this actually builds with some real examples. Here are 2 super high-yield reactions you really need to know. First up, when highly reactive sodium meets dilute hydrochloric acid, it vigorously forms sodium chloride, which is your metallic salt, and hydrogen gas. Second, when calcium reacts with dilute sulfuric acid, it produces calcium sulfate, another metallic salt, and hydrogen gas. Do you notice the pattern here? The metal basically just swoops in, steals the non-metal part of the acid, and kicks hydrogen out into the cold as a gas. It's a very reliable, very predictable trend for your highly reactive metals like sodium, potassium, and calcium.
Section 4. Displacement reaction dynamics.
Now, in a displacement reaction, a more reactive metal kind of acts like a bully on a playground. It physically displaces a less reactive metal right out of its salt compound. Let's walk through a really classic lab scenario. Step 1, you take a highly reactive metal like zinc and add it to a solution of copper sulfate. Now, copper is much lower on the reactivity series than zinc. So, step 2, zinc bullies its way in and completely displaces the less reactive copper from the sulfate. Step 3, you're left with a brand new solution of zinc sulfate and the pure copper gets kicked out, forming a highly visible precipitate. And you know, beyond the exam room, this exact dynamic is used in the real world constantly. Mining companies actually use cheap scrap iron to displace and recover valuable copper from aqueous solutions. It's brilliant. So if a test question tries to trick you by asking, what happens if you put copper into a zinc sulfate solution, you can confidently write no reaction, because a weak metal cannot displace a strong one. Only the more reactive metal wins.
Finally, Section 5, the hydrogen exceptions. Okay, this is an area where so many students lose easy points, just because they assume all metals react similarly across the board. The truth is, most metals completely ignore hydrogen. They don't react with it at all. But there is a major exception. Only a very select few, our highly reactive VIP trio of potassium, sodium, and calcium, actually have the chemical drive to react with hydrogen. And when they do, they form compounds called metal hydrides. So potassium becomes potassium hydride, sodium becomes sodium hydride, and calcium becomes calcium hydride. If you ever see a multiple choice question asking which metal forms a hydride, just skip right past zinc, aluminum, copper, and gold. Look straight for those top-tier reactive metals.
To wrap up this explainer and our rapid concept review, I want to leave you with a bit of a provocative thought, just to test your newfound knowledge. We've talked a whole lot about the reactive heavyweights today, right? Potassium, sodium, zinc. But knowing these rules, the logical shortcuts we went through, and those tricky exceptions, how would a non-reactive metal like gold perform across these 5 testing scenarios? Think about it. If you dropped gold in oxygen, hot water, cold water, dilute acid, or hydrogen, what would happen? Well, if your immediate answer is absolutely nothing, then you have successfully mastered the reactivity series. Gold sits at the very bottom, completely unbothered by these chemical tests. Keep reviewing these concepts, trust the shortcuts, and you are absolutely going to crush your exams. Thanks for hanging out with me for this explainer, and stay curious.